Hello again, YouTube. I have to get back to finish off a few projects. Earning a living sometimes gets in the way. I had previous videos about a mower controller of a Tarup mower. It's an agricultural mower. This is the user interface to it. It's a 3-position latching switch and then a momentary switch with two, either down or up, and then it was a pot previously, but this is I'm using an endless encoder. There's also a switch on it. We'll get to that in the fullness of time. That's just a daughter board that pops onto a Cinnamon Bun. So the Cinnamon Bun is going to be the human interface end of it, and this is the control board for, there's 3 outputs. We've got solid state switches on 3 outputs, which will control solenoids for hydraulics, and then 2 inputs. Now, 1 input historically never worked on the mower, so I've put it on this board. I'll see if we can't work out what it should be doing, or whether it is working or not, but I was always told it didn't work. And this is the position of the auto swather. At the end of all this, I'll put it all together and hopefully have a video of it working. But so these are three outputs. The guts of this board is just a Cinnamon Bun populated into a larger board. Power supply section, CAN bus connector, the power in, and then 3 outputs, 2 inputs. But it's basically the same electronics, a different board file when I come to developing my software that goes into it. Now, before I get into the full-blown adding on human interface, I wanted to get into the actual basics of using CAN bus on this Libby soup thing. CAN bus is just a 2-wire differential signal protocol. So you've got a CAN high and CAN low. So CAN high and CAN low are just connected together on the various nodes on the bus. Now, the number of nodes on a bus is limited by certain physical restrictions. I'd have to look up the data sheet for the physical transceiver. Is that little chip down in there. That is the limiting thing. There'll be a limiting thing in terms of the physics of that network. You've got a 30 meter. The CAN bus was originally spec'd for the automotive industry, so it's 30 meters. Originally there was 11 bits of a CAN identifier. The extended CAN 2.0 gave a 21-bit identifier, as far as I remember. Now, one thing that I probably shouldn't have done, or I should have added to this, is that the CAN bus is terminated by there's a termination resistor on each end of the bus. So I don't actually have them on the Cinnamon Bun, because I always kind of felt it would be part of the actual physical network. So I've just added on, soldered on 120 ohm resistors in this case to terminate the bus. Now, there is different termination. There's different circuits that sometimes there's a split between. I think you can put 2 or 3 resistors into the termination. I'm just using a simple 120 for the minute. And I've got these things connected to. I had put them in a. I'm trying to get them, going to fit them in a box. So this is the side that goes in the tractor. So this is the human interface, and it's powered from these 2 wires coming in. So power is coming in 12 volts, and I just soldered it into. I don't actually have connectors like this, screw terminals designed into this development board, so I've soldered it in for the minute now. So power is coming in and then goes straight back down through this. So the data on the CAN bus and the power back down goes to this, the unit which is actually doing the control. So I just use an Eco 5-pin connector to connect these 2 together. So what we have then is 2 nodes on a CAN bus. And this connector is transmitting everything down. So power, ground, and CAN high and CAN low are going down through this bus, which is terminated by 120 ohm resistor. Now, just to get started with, before we get too complicated and get into actually reading sensors from this or whatever, we'll do a simple walkthrough of the actual API and how you use CAN in this API, in the LibESoup API. So if I go to a piece of simple code, this is my transmission side. So this is the side that goes into the actual cinnamon bun, this small unit. And I'm going to have it transmit. So basically, I'm forward declaring an expiry function which is going to handle a timer. So a timer expiry is going to happen. There's also a status handler. The CAN bus, various status changes at a low level, which are going to happen asynchronously. We've no idea of the timing of CAN bus in terms of how often and when events happen. So it's an asynchronous handler. So this is a timer handler forward declared, and this is a status handler. Now the status handler is doing nothing, as you can see. It just is an empty function. But when we initialize the CAN bus in this libESoup library, we have to give it a status handler function to process events from the system. There's other events from other parts of the system, but for the minute we're just talking about CAN bus. So we initialize the library, initialize CAN bus with the system handler, and we're selecting a baud rate of 250k. We can go to 1 meg, but we'll leave it at 250k for the minute. So all this transmission side, this is a little piece of test code. All it's going to do is fill out a timer request structure. So we want a 10-second timer, and we want it to repeat. So it's a periodic timer. Every 10 seconds we want to call the expiry function, expiry, which we declared up above. And that's all this code does. This code is purely event driven. So now we just, in the infinite main loop of this microcontroller, there is no multi-threading, there's no multitasking, there's one task, one infinite loop, and all it does is process events from the system, and the only event that we're creating is a timer. So we're periodically going to get this function called, this expiry function. And all this expiry function does, it creates a CAN frame and fills that CAN frame out. Now the DCL, this is standard nomenclature in CAN bus protocol. DCL is the number of data bytes. I can't remember the exact term of what that stands for. DCL is, can't think. So we're filling out a stripped down frame. We can have up to 8 data bytes in here. We're carrying none, and the frame is going to have a standard identifier of hex 700. Now the original CAN bus 1 protocol had 11-bit identifiers, so we've got 1 1 1 and 8 zeros, and all we do then is pass this in this API call to the libESoup, so that libESoup library, and say, right, transmit that frame. So anytime this event, this timer event happens, transmit this frame on the network. Sorry, not a network bus. It's more of a bus structure really, but network bus, potatoes. So that code is sitting in, like I say, this straight cinnamon bun development board. The other side of the bus, we have our control board, which is actually has the output, the electronics for the output, the solid state outputs, and the sensors. Now for the minute we're just doing a piece of test code here, but so same thing again. In this case I'm going to forward declare a frame handler, and this is going to process CAN bus frame events. We'll get to that in a minute. Now the other main, I had a system handler for system events that was empty. In this side, I'm using serial logging on the serial port, so we're adding in. It's not really handling much of a system status, but it is actually giving us some indication of what statuses are happening. Status messages. Now, when the system powers up, when the bus powers up, or when the nodes on the bus power up, they have no idea what's happening in terms of like when we initialize the in this side this is the receiving side. We initialize libesoup, the library, again, and we initialize the CAN bus with 250k. Now the system is, the code brings up the bus, or the CAN bus, but there's no indication of whether that bus is actually operational. In the protocol, it's a multi-master protocol, so we can have 10, 20 nodes on that bus, and any one of those nodes can be the master. Any one of those nodes can decide, I have a frame to transmit. When it decides it has its frame to transmit, it basically starts transmitting. Now there's collision detection, and nodes will back off if nodes try and transmit at the same time. This isn't going to happen in this case because we've only got one transmitter and one receiver. But normally a node can transmit and receive at any time it wants to transmit. It just grabs the bus it grabs the bus and starts transmission. So we bring up the CAN bus, 250k is the baud rate we're selecting, but we've no idea what the status is. So when we receive a frame or transmit a frame and get an acknowledge, when somebody grabs the bus as a master and transmits a frame, somebody out there on the bus, another node has to acknowledge that frame. As soon as somebody acknowledges a frame, then we know the bus is up and connected. So we're connected to the bus at that point. So on the other side, if we receive a frame, if a node receives a frame, then it will acknowledge that frame. It's received it, and then it's connected. It knows, well, I've got a network or I've got a bus. So initialize the library. Initialize CAN bus with 250k. I should say that it's been a while since I did a video, but the library is defined by this configuration file. libesoup config basically sets what the system is, 60 meg clock. We want to enable hardware timers, we want to enable software timers, and we want to have up to 10 software timers. Now this is C. When it's compiled, the compiler will allocate resources, so memory will be allocated for 10 timers in this case. And we want the top timers to be, the software timers to be a tick of 5 milliseconds, so we've only got a resolution of 5 milliseconds. We're using a 10-second timer, so if we're out by 5 milliseconds, it's not going to be, I mean, if we're less than 5 milliseconds out, it's not a big swing. We're using the UART for serial communications. This is our debug, so we're debugging at 19K2 baud, and change notification is change on GPIO pins, so we can automatically be notified of changes on a pin. Now this is, we've got two inputs, two digital inputs, so that's why there's on this board the two inputs, the 3-pin input and that 2-pin input. That's why we've got a change notification defined to 2. We want change notification enabled, and we want to monitor 2 things. And we've got an ADC channel. We'll come back to that. But the other thing is the CAN bus. We've got a CAN bus and we want a frame handler size. So we want to be able to handle 10 different frames. We'll see that now back in that main, which is doing the reception. We are initializing, and this target is a CAN bus target, a frame target. It's a layer 2 frame. So there's layer 3 protocols which we will get to in time, but for the minute we're talking about layer 2 frames, which is a single CAN frame with either a standard 11-bit identifier or an extended 21-bit identifier and 8 bytes of data. So this frame, we give it a filter and a mask and say, right, we're interested in frames with the identifier 700 hex, and we want this as the mask. So each bit in this mask which is 1 we're interested in. So we're going to have 4 ones at the top. So that's 7, 8E. So that's saying we don't care what the last bit is. If we receive the frame 701, we want to receive that. Similarly, if we receive 771, we want to receive that. And that's just the way this is encoded in the CAN specification. And it's the DSPIC I'm using implements the protocol, and this is what it's implementing. It's implementing a master and filter for frames that we want to receive. So we're saying you can actually put these master and the mask and filter into the silicon, put it into a special function register of the DSPIC 33 and let it handle it, or you can handle it in software. The implementation is really neither here nor there. So basically we're declaring our interest in a frame. Now, so if the transmitter, or if another node on the network transmits the frame is hex 800, this node will acknowledge that frame. It's received a frame. But then it will look at 800 and go, well, it's not 700, I've no interest in it, and dump it. So that no action will be taken on that message. So as part of this task, this target, layer 2 CAN target, we've master, filter, we've got a handler now as well. And that was the frame handler, the forward declaration up at the top of our handler function, which is going to handle a CAN frame. So it takes one parameter, which is a pointer, the address of a CAN frame. And all our frame handler has done is just print out the identifier that it's received. Our transmission side is event driven in that it's doing nothing except looping and processing the libEsup tasks. On this reception side, we're doing the same. I've put in a no-op and a check of the return from libEsup tasks, but let's just assume it works. It's only a piece of test code, so I'm not too worried about it. But so it does the same. It's an infinite loop. It processes events, or it checks the hardware for events, either timer expiry or CAN bus frames in this case. And anytime there's a frame that fulfills these requirements, then this handler function is going to get called, and that's it. So like I say, that code is in these two nodes, transmit and receive. I've got the serial debug cable on the receive side, so we're not going to see much on there. We're going to see more here, and that's just noise from me faffing about. So if I power up this whole bus structure, so we've initialized the CAN bus 250k. We've got a status handler connecting because like I said, we haven't received anything. Now we've received something. So now we've gone to the connected state. and we've received a frame which is, it's got the CAN identifier 700. And that's just a very simple look at CAN bus. Now that identifier I'm using, 700, I could have used anything. We're working on our own solution to something. I mean, in the automotive industry, which CAN bus was created for, the OBD2 and various diagnostic ports use CAN frames, and the message, the numbers, the CAN identifiers in those messages have specific meanings. They're to do with brake sensors and they're to do with engine management systems. Now, there are proprietary numbers, or there are numbers that have fixed meanings, and then there are other numbers, identifiers, that a manufacturer can use for whatever they want. In this case, we're not interfacing to a standard piece of equipment. We're just interfacing between ourselves, so we can do whatever we want. So 700 can mean whatever we want it to mean. And we'll get to that when we add on our input and actually process those inputs, take the inputs and the changes on the inputs and transmit them down to our actuator, which is going to control the electronics, which is controlling hydraulics and electronics. So that's it. That's just, I wanted to have a brief look at the API and how it's working. I mean, the transmission side is fill out a frame, declare the data length, and if we were transmitting bytes, it would be fill out the data bytes, fill out an identifier, and just call the transmission function. On the reception side, we just say, well, we're interested in this frame. Now, we can have any number of, well, not any number. In the header file, the configuration header file, I've said I had an interest in 10 different frame handlers. So we can declare up to 10 different handlers, register 10 handlers with different messages, message identifiers. So now we could, there's numerous ways you could solve this problem that, well, not problem, but this, call it a problem, like we've got a transmission side, a reception side, we've got a human input on one side, and we've got actuators on the other side, changing the electronics. We could send all messages as one identifier and put in different data bytes, and the 8 data bytes that we've got, the payload, we could put in whatever different bytes, or we could declare 10 different identifiers and use each identifier for something different. So we can put out whatever solution we want. In this case, we've got a blank canvas. We'll get to that in the next video. I'll leave it there for now. Thanks a million for watching.